Good morning to the audience here on site. Good morning to the audience online. Welcome to my little presentation on microwave chemistry for the analytical laboratory. In fact, we'll specialize on sample digestion for elemental analysis. My name is Peter Kettisch. I'm head of the analytical and synthetic chemistry product line, which is one of 15 product lines from Anton Paar. I'm based in our headquarter labs in Austria, in Graz, and I'll show you at the end of my presentation a few pictures of Graz that you get an impression where I'm coming from. Content of the talk today will be a few words about Anton Paar first. You should know that there's a proper company behind those beautiful machines. Short section on fundamentals and challenges in sample preparation, and the main part will be going to the introduction of our Multiwave family of products for sample digestion, and mainly I'll spend time on application examples because I think this is the thing you are most interested in. At the end of the presentation on screen, we'll do a little hands-on section for those who are here on site, so a short live demonstration. Of course, we can't do a complete digestion, but I show you the simplification of handling of vessels and ovens. And at the end, I'm open for a Q&A session. I think you can also submit questions online that we will collect and answer later on. So thanks for joining. First, Anton Paar, who are we? This is a picture of our headquarters in Graz, Austria. We just celebrated our 100th anniversary, so founded in 1922, headquarters in Austria. Globally, we are about 3,700 employees. Almost half of them is working in Austria, in Graz. The others are working in our subsidiaries and doing mainly sales and service and support of our instruments. The company is owned by a charitable foundation, and we are driven by innovation. So we are reinvesting 16% of our turnover of the headquarter lab into research and development. And this is why we are always at the cutting edge of the technologies that we provide to the market. Another specialty of Anton Paar is that we produce a lot of the components in-house. So we have a strong manufacturing section for electronic and mechanical parts. So we keep all the core technologies to build our instruments in our own hands. The Anton Paar Group has currently 9 producing companies in 6 countries. The main part is in the headquarters in Austria. We have 33 fully owned sales subsidiaries, and in the countries where we have no subsidiary, we work via distribution partners. So we are present globally, and this is an important basic of our business to be close to the customer, because the products that we are providing to the market, they need some support, explanation, and support in the application. So we are close to the users and support them in proper use of our instrumentation. Just one slide on our corporate service standards, which I think are important to a user of instruments. We are proud of our quick response time. So it's our company standard to respond within 1 business day. We are aiming for customer satisfaction. So our CEO has given the limits of maximum 1.5% unsatisfied customers, which is really low for our kind of business. And we expect to get feedback on our services from more than 25% of our customers. And in fact, we are able to keep these limits. We are also aiming for a short case time. That means we are completing repair and service actions within less than 7 days in 3/4 of the cases. That's important for us. Availability of spare parts. Anton Paar warrants the availability of spare parts for 10 years after discontinuation of a product. So you are safe when you buy. This is a future-driven investment, and you get support and service for a long time. Now let me show you a long time how long Anton Paar works in sample preparation. So this product line is one of the traditional ones of Anton Paar. started in the late 1970s. Beginning in 1990, we started with microwave technology. So this timeline here is Anton Paar's history in microwave technology. More than 30 years. So you can imagine we gained a lot of experience, and all this has materialized in a group of products which are at the state of the art in sample preparation with microwaves. So these are the products I'm talking about shortly. First, let me give you a short summary and reminder about the fundamentals of sample preparation, why we are doing this at all. So, sure, most of you will be aware that we need to convert solid samples into a liquid measurable form. So the transformation of solid samples into measurable liquids, liquids that are in a chemical and physical style of, let's say, the calibration solutions that we use to calibrate our measuring instruments like the ICP here. So we destroy the matrix, we separate matrix and analytes, we get rid of interfering substances. Think about carbon from organic samples that we remove, or the silicates from mineral samples. We separate those elements that would disturb our further analysis. For doing this, there are mainly three groups of methods. The most widely used is acid decomposition. Dissolving samples in acids, you could either do this in open vessels on a hot plate, or you could do this in pressurized vessels in a microwave. Why pressurized? Why microwaves? I will explain in a minute. Acid digestion is the most universally applicable form of sample preparation and used in almost any elemental analysis labs around the world. In the mining industry, maybe some of you are working with fusion or fire assays, very widely used for geological samples, and for a certain type of organic material, also combustion and ashing, burning with oxygen or ashing in a muffle furnace is still in use. I would like to focus on closed vessel digestion with microwave heating because this is the most trendy type of sample preparation nowadays and, like I said, most widely applicable. When we talk about digestion, it's a question, do we do it in open vessels, beakers, hot plates, or do we do it in closed vessels? The limitation of open vessel digests is mainly the boiling point of the reagents. So if you do it with nitric, you are limited at 122. Of course, you could add some sulfuric to the mixture to increase the boiling point. On the other hand, sulfuric acid is disadvantageous for the ICP analysis. So keep the chemistry simple, use as few acids as needed to completely digest the sample, and try to take the acids to higher temperatures. That's the reason why we go to closed vessels. The pressure, it will allow the build-up of pressure, therefore allow higher temperatures. It's like the pressure cooker principle in the kitchen. So temperatures above the boiling point at ambient pressure, that's the thing we want to achieve. Further benefits, closed vessel digests do not allow any loss of analytes. They keep the analyte safely contained. And also the contamination level is minimum and the reagent consumption is minimum. So there are a lot of systematic benefits when using closed vessel digests. Why do we want high temperature? Of course, for saving time and for the sake of completeness of the reaction. So the higher the temperature, the lower the time consumed to complete the reaction. So this is expressed in the Arrhenius equation, as all we as chemists know. Expressed as a rule of thumb, it means 10 degrees increase in temperature will double the reaction speed. And what that means is, for instance, a reaction that would take 8 hours at 100 degrees could be completed within 8 minutes when we can take the same reaction to 160 degrees. So it's simplification, time reduction when we can work in systems allowing higher temperature. This already takes us to the matter of today. It's a visualization of a digest of an oil sample at different temperatures. Same time, different temperature. So if we digest this oil sample, lubrication oil, at 170 degrees, left-hand picture, we see there are still solid particles in there, brown charred material, which did not dissolve. So this is not appropriate for analysis at all. Doing the same time at 190, you see a strongly yellow colored solution, no particles anymore, but nevertheless the yellow color already indicates there's a lot of undestroyed organic substance in the solution. Take the same thing to 230 degrees, slightly yellowish coloration. That's a solution that I would dare to use on an ICP. Still some residual carbon in there, but the ICP will burn that anyhow. The ideal way, you see here, a digestion at 260 degrees, a water-clear solution. This is what we call a complete mineralization of the sample, and this is the ideal condition for trouble-free analysis on the ICP. The more carbon you introduce to your ICP, the more soot deposits you will have on the torches in the torch compartments, the more cleaning efforts you need to apply, and the more measurement interferences you may have depending on what kind of alloys you're looking for. And this may be less critical for ICP optical emission analysis, but ICP MS is particularly sensitive to residual carbon that may form cluster ions in the quadrupole analyzer. Maybe you will ask, why microwave heating? Well, the benefit and the beauty of microwave heating is that we can turn the heat instantaneously on and off. Compared to classical heating via blocks or plates, where the heat is applied via conduction and convection inside the reaction vessel, the microwave acts differently. It directly interacts with the liquid molecules inside the reaction vessel, and of course you must place the sample into a microwave transparent form of vessel. So microwaves penetrate through the vessel walls and interact directly with the filling content. So this leads more or less to an inverted temperature gradient. So the liquid is hottest at the inside and gets cooler to the outside. Completely contrary to as if we would apply the heat from the outside in a block digester. So this is of course beneficial. How do microwaves heat? How do they provide heat directly to our sample solution? Well, there are two mechanisms. One is dipolar rotation. Dipolar rotation means polar molecules would align with the frequency of the microwave field. Microwaves used for laboratory purposes usually act at the frequency of 2.45 gigahertz, so this is a very high frequency, and this high frequency of rotation of the molecules you can understand as molecular movement, and molecular movement is heat. So these dipoles align to the electromagnetic field. The other mechanism is ionic conduction. Free ions in the solution would move in the frequency of the electromagnetic field, and also this free movement is molecular movement is heat. The ionic conduction is dependent on the concentration of free ions in the solution. And this is, by the way, the explanation why distilled water would not heat very well in the microwave, whereas if you put just a small portion of, let's say, nitric acid into it to add some free ions to the solution, this heating mechanism works very well. Having said this, I must mention that you cannot heat each and any substance in the microwave. You need polar substances. Fortunately, all the acids we are using for sample decomposition are polar and have a lot of free ions, so the heating mechanism on acids is very efficient with microwaves. You can imagine also doing solvent extraction in a microwave, and there you must be much more careful because not all the solvents would be polar. I'll talk about solvent extraction later, but just now give you an explanation why not all the solvents can be heated in a microwave. But luckily, all the acids do. Now, why do we use pressure vessels? Why can't we boil open on a hot plate? We said already we want to increase the boiling point. However, the high temperature leads to high pressure. Where does pressure come from? Imagine you have sample hydrocarbon material that is treated with acid and heated up. So it will lead to a reaction. Gaseous reaction products will occur, CO2 from the carbon, nitrous gases from the decay of the nitric acid, and there will be some residual liquid which develops some vapor pressure. So the pressure inside a closed reaction vial is the addition of the partial pressures of the gaseous reaction products and the vapor pressure of the liquid. Now, what implications does that have? Gaseous products, that's the things that produce pressure. And it means the higher our sample weight, the more CO2 we are producing, the higher the pressure will get. This is a little bit the downside of closed vessel digestion. So the question would be, can we somehow get rid of the gaseous products whereas retaining the liquid that contains our analytes? This is the basis of a concept that we have developed that we call smart vent. The smart vent vessel concept works with controlled release of the unwanted gases, but retaining the liquids and the analyte inside the vessel. What you see here on the right side of this picture is a cross section through a screw cap of a reaction vial. The red part here is the sealing cone, and in the upper part of that screw cap there is a spring-loaded mechanism that applies certain pressure onto the cap and onto the plug and onto the vessel. What happens when the pressure from the gaseous reaction products internally reaches the design limit of the vessel? Then this red plug will be pushed upwards a little bit, and the gaseous reaction products will escape through this part which is marked with the yellow arrows here. Such a vent and reseal mechanism will release the gaseous reaction products but will retain the sample solution at the bottom of the instrument. So it is a very short and quick release of overpressure of unwanted gaseous products, and then the system quickly reseals and continues operation and heating. And therefore, we achieve only the vapor pressure of the liquids down here in the vessels and can therefore go to higher temperatures. Practically, such a design also allows higher sample weights for the very same reason. And it is, on one hand, a functional principle. On the other hand, it's also a safety feature, because if a sample reaction would go very rapidly, maybe explosion-like, this pressure, which could cause a safety concern, would also be safely discharged through this venting path. So comparing a closed vessel digest, imagine we want to take our sample up to a certain temperature along a heating ramp and keep this temperature for a while. This would be a typical course of a digestion reaction temperature profile. And imagine we have a pressure limit at a certain number of bar. When we heat up at a certain point, the pressure inside due to the digestion reaction will increase, and when it has reached the pressure limit of the vessel, sensors must act and limit the temperature and not heat further up in order not to overpressurize. This is what happens inside a completely closed pressure vessel. If we apply smart vent technology, it works pretty much the same up to this point, but here, due to pressure relief action, the temperature can increase further. And like said before, the maximum temperature is the important thing we want to achieve for complete mineralization. So this smart vent technology helps us to achieve higher temperatures without running into overpressure problems. Before we come to instruments and vessel designs and applications, just a few words about the pain that is involved with sample preparation. I think you are all aware of that, and I would say there are mainly three concerns: economic, safety, and analytical concerns. So the economic concerns is mainly the time consumption, but also the instruments investment, instruments maintenance, breakdown, availability issues, things that are influencing the sample throughput of our lab. So how to cope with this? You can imagine that high-performance digestion instruments with modern, reliable technology can reduce time consumption for the very aspects I explained right now. Robustness of instruments, regular maintenance, and a reliable service provider will ease this pain. I think performance of instruments and availability of local service, they are of equal importance. How's about safety concerns? Like said before, pressurized reactions, maybe spontaneous reactions may occur, and very often it is the skill and knowledge of the lab staff which is most important to deal with difficult samples in a safe way. So training and support from the vendor of instruments very often is a key issue, and we see this especially in labs with a lot of staff turnover. It needs permanent retraining to utilize instruments in an optimal way. Concerns about corrosive or toxic reagents or reactivity of samples, you can get along with these very well when you work with stable, safe, and easy to handle systems, and when you apply reliable sensor technology for reaction control. Either control pressure and temperature, or use only temperature control and the smart vent system, which is the easiest to handle system today. Last but not least, the analytical requirements. Of course, we must aim for low blank values, no contaminations, especially for accurate analytical results. And what we as an instrument manufacturer can do to help you on that point is we provide you with proven methods, with application reports, with methods pre-programmed on the instruments that are ready to use and lead to correct analytical results. So I hope this was just a little reminder for most of you, because I think you're facing these things in your daily lab work almost every day. Now, maybe this is something new to you. That's the presentation of Anton Paar's solution for sample preparation. And I'm presenting to you the Multiwave family of instruments. We are offering 3 different kinds of microwave digestors that I'm going to explain and introduce with application examples to you right now. So you see we have 3 different instruments. Why that? Because when you consider the various things influencing your purchasing decision, you may decide for one of them depending on your lab requirements. And the lab requirements first are mainly the analytical requirements. What samples do I have? What analytes I'm looking for? What is the analyzer? Do I use AA or ICP? How sensitive is it to residual sample components? What kind of acids, what kind of chemistry can I apply and feed into my analyzer? So this is the first consideration. Very often, second is sample throughput. Am I a high throughput laboratory, or do I have to analyze just 5 samples a week? Then it's handling and usability. How complex is the machine that I have for sample preparation? Of course, we want to have it as simple as possible. We have to deal with the analyzers anyhow, so at least the sample prep should be easy. safety and reliability. Even if we do something wrong, the instrument should have safety provisions that do not allow it to run into unsafe conditions. It's a question of costs of ownership. I'm really focusing on total costs of ownership, not just on the purchasing price, because you will see even a more expensive instrument over a long period of time, due to the savings that you have in operation time, handling time, savings in reagents that you need to apply, can already compensate for a higher purchasing price. And last but not least, like I said before, service and support is an important issue, that you are satisfied with the microwave that you've purchased for your laboratory. First thing that I want, first of the three machines, is our Multiwave 5000. This is not just a digester, it is a laboratory microwave that can do various other sample preparation tasks as well. It's the thing that we have here on the table that I will show you later. This Multiwave 5000 allows, beside acid digestion and acid leaching, also evaporation of solutions. It allows drying of samples prior to analysis. You could do oxygen combustion of organic sample materials. It can be used for organic chemistry, solvent extraction, derivatization, protein hydrolysis, and things like that. I will not cover this part today because it would exceed the scope of our seminar, but just want to make you aware, if you're interested in such organic chemistry applications, also involving organic synthesis, this is a separate part of our business. The Multiwave 5000 can do these reactions as well. What's special with this machine? It is a standard laboratory, state-of-the-art laboratory microwave oven, solid stainless steel cavity, stainless steel safety door. It has a cavity size of 66 liters, so various rotors with many samples could go into this huge cavity. It has a strong installed microwave power of 2000 watt. This allows for very efficient heating, but it's not just heating, it's also cooling very fast, because it has an integrated cooling unit, and we will understand the use of cooling later when we see the applications. On one hand, the cooling unit helps us to cope with spontaneous exothermic reactions, and on the other hand, it helps us at the end of the digestion to cool down to safe temperatures that we can take out the vessels and open them quickly. The cooling unit integrated, powerful thing. Very useful for the user is the built-in methods library. It comes with more than 500 ready-to-use applications and methods built in. So I'll show you later. Just type in the sort of sample you have, and the instrument comes with a recipe. Tells you what acids to apply, what temperature profile to apply, and you just load the vessels in that style, press start, and do it. So the state-of-the-art software and user interface helps you with all these tasks. Last but not least, a very nice feature is the hands-free door opener that I'm going to demonstrate later on. Imagine when you come with your rotor to the microwave, you do not want to set the rotor aside to open the door, but in our case you come with the rotor, check the door with the elbow, and it will open automatically and you can insert the rotor. So that's a nice little detail that our users like most. Another thing to talk about is the ultimate safety this instrument provides. And it starts, for instance, with the use of reliable sensor technology for temperature measurement. Temperature is our primary factor that we need to control. It continues with a stable stainless steel door. Even if we control temperature precisely, there may be some samples of unknown reaction behavior that react spontaneously. And in such a case, like said before, the vessels would open, would give way to the overpressure, and if it is a very serious and sudden discharge, also the open door would slightly open, let the pressure escape, and reseal immediately, and of course shut off the microwave in such a case. So this safety door, the vent and reseal safety door, is another important feature of this Multiwave 5000 instrument. During the process, the microwave door is locked. So once the vessels are hot and pressurized, it is not possible to take them out. So you won't get access to vessels in a dangerous condition. Active door lock. Of course, there are a lot of other thermal and mechanical interlocks. Last but not least, most important, we do not just say this as a manufacturer, but we have third-party testing labs, Intertek, that were testing all our sample preparation devices for instrumental safety. So we get certification from this third-party lab that our instruments comply with the provisions of the machinery directive, which is the most important safety norm for instruments in the lab. Application-wise, we also comply with international standards. This plays an important role for our customers in the pharmaceutical industry. So we, for instance, comply with the provisions of the US Pharmacopoeia and with many other pharmacopoeias in other countries. We offer pharma qualification and validation packages for this machine, but not only for the pharmaceutical customers, also in elemental analysis for environmental material, for food materials, for material testing in general. There are methods like US EPA, ASTM, AOAC, or European or international standard methods for sample digestions, which are preloaded on the instrument. And you just switch to, let's say, ASTM 3546, which is, by the way, a solvent extraction norm. You look to the methods library, load your vessels appropriately, and run it. Many of our users are using these pre-programmed either standard methods or Anton Paar optimized methods, but of course, if they like, they can extend the method library with their own methods. You can always use methods, modify them, restore them as your own user methods. So we're very flexible and can grow the methods library over the years. Now, the performance of this Multiwave 5000 is mainly determined by the sort of pressure vessel and rotor that you apply. This is the selection of 4 different smart vent rotors that we can use in Multiwave 5000. These are rotors, for instance, with 24 or 41 places, high pressure vessels, venting technology. The number at the end is the volume of the vessel. It's either 50, 56 or 80 milliliters. Why would you use 80? For larger water samples, for instance. The preferred choice of users is smaller vessels, 50 or 56 milliliters, because they are easier to handle on the balance, easier to clean. The smaller the volume is, the better it is for analytical purposes. Less surface that could absorb analytes, less surface to clean. For the more difficult type of samples, we use a rotor with 20 positions of superior high pressure, 50 milliliter volume as well. Like I said, the 50 milliliter has almost become a standard vessel size for sample preparation chemistry. Just a summary for those who are online and not with us in the live presentation here. Just to give an impression how these smart vent vessels look like. They consist of a vessel body, a sealing plug, and a screw cap that goes on top. It's just these 3 parts to assemble and to handle to have a fully operational high pressure vessel available. That's one thing, the ease of handling. Second, like I said before, is the overpressure release via discharge openings here at the top. It is the robustness. If you look at these sealing plugs, there are no parts that can get destroyed. So the lifetime of these components is very long. We're speaking about several hundreds of digestions. We have users doing 1,500 and more in one set of vessels. And the other thing is the air gap cooling. When you look at the vessel bodies here to the lower right side, they have cooling fins at the outside, and between these cooling fins we are forcing cooling air to flow across. And like I said before, this instrument has the built-in cooling unit. Along with these cooling fins, it gives a very efficient cooling at the end of the digestion. And another beneficial thing is you could even load the rotor inside the oven. So you would not have to carry a large rotor with you, can leave the rotor body inside the oven and load individual vessels into there. First application examples I'm going to show you at the example of a 41 place rotor, which is used in high throughput laboratories. It is good for routine samples. Routine samples, easier to digest organic and inorganic materials that can be decomposed properly at temperatures of up to 200 degrees centigrade at a controlled reaction pressure of 20 bar. So this is the most important characteristics of a reaction vessel: temperature and subsequently pressure. 41 samples in one run. What is the scope of applications for this kind of rotor? Well, it's the easy to moderately difficult to decompose samples. From food and feed, biological materials, plants, environmental samples like water, wastewater, sewage sludge, soil. It is used for total digest as well as for leaching. Leaching, as you know, is a partial extraction of elements of interest, whereas it leaves part of the sample undestroyed. Classical example, leaching of a soil sample with aqua regia. You would leach out all the elements of interest but leave the silicates undestroyed. Very common technique in environmental labs. So no wonder that this type of rotor also is approved for EPA and other standard procedures for environmental and food testing. It also can cope with cosmetics, pharmaceutical samples, metals, and some of the geochemical and mining samples. A typical temperature profile for food samples, for instance, would be a ramp up to 180 degrees over 20 minutes and hold at 180 for another 10 minutes and then cool down to 70 degrees. So the actual digestion time is only 30 minutes in that case. Add cooling 15-20 minutes. So within 1 hour, including loading and unloading the rotor, a set of 41 food samples can be done. Chemistry, like I said, was simple. Half a gram of sample, 7 milliliters of nitric, and some of the analytes may require a small portion of hydrochloric acid for keeping them in the solution as chlorocomplexes. This is a printout that you would get at the end of such a reaction, and what you see is, as we have used a mixed set of food samples, very sluggish in reaction to very quick in reaction, you see that the temperatures developed in here were quite different depending on the reaction nature of the sample. There were some exothermically reacting samples that are showing temperature peaks right here, and there were blank samples that followed exactly the pre-programmed temperature. From this picture you can see you had a set of samples that reacted quite differently. That's okay, the instrument is made for that. The important thing is that you take all your samples to the desired end temperature of 180 degrees, because within this period of time the final mineralization takes place. So no matter how the course of the reaction is at the beginning, at the end all these 41 samples achieved the same desired end temperature. Then you see it's about 15 to 20 minutes to cool down. This is what you get to see on the screen of the instrument after the digestion. What you get to see after ICP analysis, and we intentionally tested the accuracy and the efficiency of this digest by analyzing reference materials, food materials like the spinach leaves or oyster tissue, and you see for a large set of elements very good agreement of what we measured to what was certified for the reference material. So recovery rates of 90 to 100%. This is within the normal scope of what you can expect from such a digester. Maybe you say, I'm missing a few elements. Of course, we cannot analyze all the set, but there are critical elements, for instance, like arsenic. Arsenic, you know, might be quite volatile when you cook this in open vessel digest, but look at the arsenic values here. It's found already with more than 100%. Or also with the oyster tissue, arsenic was fully recovered, although we had such venting action of unwanted CO2. So we can make sure that this functional principle of the smart vent vessels is analytically verified. And you can get a lot of application reports from Anton Paar, including analytical data that you can reproduce with this machine in your laboratory. Another type of applications is pharmaceutical stuff. Elemental impurities in pharmaceutical products. This has been a big group of applications in the last years because many labs modernized their sample preparation facilities due to new requirements, mainly coming from the US pharmacopoeia. Again, we tried a mixed set of samples. We used, for instance, pain-killing tablet, the classic acetyl salicylic acid. We used a dietary supplement capsule, fish oil capsules. They are very widely in use worldwide. And we used cold syrup, which is a mix of alcohol and sugar. So you can imagine, if you have some experience with sample preparation chemistry, alcohol, sugar in a sample would lead to very violent reaction. And we intentionally combined these three different materials to show the performance of the microwave digester. Analysis is classically for cadmium, lead, arsenic, and mercury. These are called the big four in elemental analysis in the pharmaceutical industry, and they are mandatory to be analyzed in all pharmaceutical products that are delivered to the market. Look at the table to the lower right. Depending on the nature of the sample, the reaction chemistry was varied. So for the pain-killing tablet is a straightforward a nitric acid, little hydrochloric, and a little bit of water. Why water? In this amount of water, we added a spike solution. Because what we did for the pharmaceutical samples was spike tests. Spiking the sample and check the recovery after the digest to see if the digest was complete and if you did not have lost any type of analyte. Pain-killing tablet, dietary supplement. What you could see with the cold syrup is a bigger portion of water added to the solution. Why that? Because with this water we are somewhat diluting the alcohol in the sample, because the alcohol would react very, very violently with the nitric acid at elevated temperatures. So sometimes it is necessary to reduce the oxidation strength because the instrument would be very powerful in heating, and in order not to react a certain sample, we reduce the reactivity by the addition of water. Again, we have a look at the temperature profiles programmed in a way, in a two-step way. First, a short heating ramp and a heating plateau below 100 degrees for the initial reactions to take place, and then heating up to 180 and hold it for another 30 minutes. What you can see here from the course of the reaction, the curve to the right, the red curve to the right, is you see a temperature peak here. And we already know this comes from exothermic reactions inside the vessels. So the instrument recognizes that it's a very severe, very spontaneous reaction going on. but it can cope with it. You won't face any problem from that. When we look at the spike recovery elements, and this is now for a little bit hard to read, but for the elements cadmium, lead, arsenic, and mercury, you see that the recoveries, which a USP says must be between 70 and 150, this is a very wide range. In fact, we managed to be at around 100 plus 2 or 3 minus 5 to 6% recovery. And this is indeed very good. And maybe you have missed the mercury in my previous slide, because you know that mercury is the most critical element in terms of losing it out of a digest. So if we would spray out sample solution, we would never find mercury. Finding the mercury indicates that our smart vent system, like explained before, works analytically very well. So we find full recoveries. In the table here to the right, you see the RSDs of these experiments, and they are also in most cases below 5, in most cases even below 3% RSD for 3 replicates. So this is just to show you the analytical reliability of the smart vent concept. If it comes to more difficult samples, like said before, maybe these high pressure systems would not be high enough, and we must go to even higher, superior pressure ranges. Again, we do this in 50 milliliter vessels that can be taken to 250 degrees at 40 bar controlled venting pressure. So this is another range of performance that we are opening up with this type of rotor. At that time, I would like to say a few things about sensor technology. Like said before, temperature is the most important primary parameter in sample preparation chemistry. And we have 2 types of infrared-based contactless sensors that are built into our Multiwave 5000. One is a classical IR sensor that measures the outer temperature of a reaction vessel and via a mathematical model calculates the temperature inside. This works very well when you have pressure vessels with thin walls, because then the temperature gradient from internal to outer side is not that big and the temperature transfer is quite quick. When we work with thick-walled pressure vessels, which can withstand higher pressures, we apply a new type of infrared-based sensor, which we call smart temp sensor. And smart temp more or less looks through an infrared transparent window in the PTFE material and directly measures the solution temperature inside. This is a more recent technology described in literature, and it very precisely, directly measures the solution inside without mathematical corrections. What microwave chemists did in the past, they immersed temperature probes through openings at the top and immersed these probes into the solution. Immersing probes, I would say, are not state-of-the-art anymore because of tedious handling, the risk of contaminating the sample, and all the cleaning and handling issues involved. So either classical infrared sensor or smart temp sensor is the preferred way of reaction control. What we further can do with all of our Anton Paar instruments, we can apply different temperature control strategies. Imagine you have a set of 24 vessels running there. They may have different reaction characteristics, and you can set the instrument either to control for the maximum temperature, the vessel that comes in highest, or you want to take all the vessels up to a defined minimum temperature. Then you set the control strategy to minimum, or, and this is what you do in most of the times, you just take the average temperature of all vessels in the process. Depends on what your analytical requirement is. Now, applications for the SVT rotor, like I said, more challenging samples, such as polymers, petroleum products, even including coal and graphite, minerals, alloys, pharmaceutical substances, more demanding pharmaceutical substances. So this is a wide sector of applications. There's not much that you cannot do with the SVT rotor. Let me show you the example of polymers. Typical sample quantity, 400 milligrams. You could have this in pellets, forms, or in fine powders. What is extremely useful when digesting polymers, the instrument can be applied with equipped with an optional magnetic stirrer. And magnetic stirring helps to mix samples and reagents. The difficulty with polymers, with lightweight polymers, is that they float on the surface of the acid, and when you heat up, maybe these floating polymer pellets, they would melt and form a solid layer on top of the acid, and this is unwanted because you do not have any exchange of material with the acid. When stirring such reactions, you keep the sample pellets distributed, and they offer a large surface to the acid and can be oxidized and decomposed very well. So again, what we did, we mixed different kinds of polymers in one run. I'm mentioning this mixed set of samples very often because this shows the performance. In a standard classical microwave that you may know from other labs, you should not do this. You should classify your samples, you should cluster them, and you should only use samples of the same reaction behavior in one run. This is less critical with our system, and this example shows various materials from, let's say, polystyrene up to PVC for qualitative tests. What we did for quantitative tests, because we also wanted to have analytical results, is polyethylene reference material, 2 polyethylene reference materials for analysis. This is the temperature profile that we applied. We can heat up very fast to 100 degrees. There's no reaction supposed to happen in that time, but from 100 up to 220 degrees, we go along a slow heating ramp, because somewhere here in this temperature range, the major digestion reaction will take place. And if we go there, if we heat there up too fast, this may lead to spontaneous development of a lot of gaseous products. Like I said, we will vent off these gaseous products, but they should be produced slowly. If you heat up too fast and you discharge a too strong amount of, or too high amount of reaction gases during the venting action, there is a certain danger that acid vapors will escape along with the gaseous products. So these slow heating ramps are more or less safety provisions in order to retain the solution back in the reaction vessel. So a slow heating ramp at the beginning you will see with many of our profiles. Then you leave the reaction for a while to decay until you take it up to the final desired oxidation temperature of 240 degrees in this case. Nitric acid, just nitric acid, 8 milliliters on 400 milligram material. Nitric acid does a very good job for digestion of polymers, and it is one program for all those samples. Quantitative results. You see the analysis of our reference materials. This is something you really can be working with in an analytical laboratory. So agreement of what we measured with the certified concentrations for a set of analytes is very good. Pharmaceuticals, again, we had pharmaceuticals already in the HVT rotor, but these were the easier types of pharmaceuticals. If you have, for instance, active pharmaceutical ingredients that are constituting of tri- or tetracyclic substances, they are way more difficult to destroy completely. And for such type of samples, it would need higher temperatures, higher pressures. So again, we did a spike test with the 4 elements of interest. We developed 4 different methods for our customers in the pharmaceutical industry. You see, like explained before, a 3-step method or a quick 1-step method, depending on the nature of the actual sample material. In this case, we optimized directly to the sample material, and also we optimized the chemistry. So it was mainly nitric, sometimes a little portion of hydrofluoric. For instance, if you have titanium dioxide as a filler, very commonly used in pharmaceutical substances, you need the HF to dissolve the titanium dioxide. And to increase the oxidation potential, also perchloric acid used in small amounts. The exact amount you can read from our application reports. Perchloric acid is used to increase the oxidation potential in cases of very hard to destroy sample materials. Again, spike tests, recovery rates of around 100%, including recoveries of mercury. So that's really very good. And also the RSDs in these spike tests were extremely low. So it's a tool for precision analysis in the pharmaceutical industry, and not only the pharmaceutical industry. Let's move to another group of samples, petroleum products. We have many users in the petroleum and petrochemical industry. The worst thing they have to deal with is this black, high viscous, heavy oils, bunker oils, fuel oils. So these black products contain a lot of polycyclic aromatic compounds, which on one hand tend to react spontaneously, but there are some other compounds in there that need very high temperature to be broken down completely. So it's a quite critical combination of part of the sample reacts fast, part of it takes much longer time for complete oxidation. Nevertheless, our trial was with 500 milligram, and in order to get these samples into the reaction vial, it was necessary to heat and stir the sample material before we were able to transfer it into the reaction vial. We typically do this with Pasteur pipettes that you can throw away after the dosage of the sample. Heavy oils, again, you have already seen such a profile before. A slow ramp, like I said, for the heavy reacting sample constituents, and a desired high final temperature for complete oxidation. It happened that some of these residues still looked very yellowish after this profile, and in such a case it's quite common to take the solution, add 1 milliliter of hydrochloric just as the final oxidizer, and heat up quickly to a temperature of 240 degrees. After such a 2-step procedure, any organic material would be destroyed up to perfection. We'll see later on the example of graphite, because graphite is an important material in battery manufacturing nowadays. But just have in mind slow ramps and a second step up to the desired final maximum temperature. This is well chosen for heavy organic stuff. What you mostly analyze in oil samples is nickel and vanadium, but also aluminum, iron, and silicon. This is what our customers in the refineries typically are analyzing for, and that's the elements the reference materials are specified for. And you see quite good correlation between reference value and measured value. Reference and measured. Other types of carbon-rich samples may be coal coke, petroleum coke, carbon black, and granular carbon in the form of active carbon granulates. Again, you see in this case a three-step procedure, stepwise, slow approach to a maximum temperature, and you see a time duration of 1 hour 15 minutes. So this is really a long time for a microwave, because usually you like to take the microwave to do short processes of 10, 15, 20 minutes. For such tough sample materials, it may take more than an hour to get them destroyed. And also look at the chemistry. We had to apply the 4-acid digest. We were talking in the morning about the 4-acid digest: nitric, sulfuric, hydrochloric, hydrofluoric. Also, this is quite common to deal with such difficult types of samples, which would also contain inorganic constituents. So these coal samples, for instance, always come with a certain portion of silicates in there, which requires hydrofluoric for digestion. But again, the aim was one program that could deal with this variety of sample materials, all in one run. Let's have a look at graphite. Like said before, it requires a two-step procedure. First, the 4-acid digest mix, and then a second step with the addition of perchloric, more perchloric for final oxidation. We are lucky that we have reference material for graphite. This is a German reference material, and you see certified values compared to what we found after the digest that I just showed you, and we find very high recoveries, very good recoveries for the elements of interest. Now let me come to a group of applications which are very important nowadays in many countries around the world. Also here in Australia, lithium-ion battery materials. Lithium mining, I know, is an important economic factor here in Australia, and analyzing the yield of lithium minerals like spodumene and others has become almost a standard task in many laboratories. When we look at lithium-ion battery materials, there are many. They are mostly lithium minerals with manganese, with cobalt, with iron, and they are used in their purified form as cathode materials in the lithium-ion batteries. We also can, for instance, analyze battery separator foils, which are used in battery manufacturing to separate anode from cathode substances. They're mainly based on polyethylene or polypropylene, sometimes with ceramic coating. So you can imagine this combination of elements that's quite difficult to get destroyed completely. So the acid mixture to do this must be well chosen according to the nature of the individual sample material. There's a second group of materials, like explained before, the graphite materials, and also other carbonaceous materials like silicon carbide, which is sometimes used as anode material. So silicon carbide, if you've ever dealt with this material, I think this is the most difficult to destroy organic substance we can do in wet chemical digestion. Battery materials for the sample group 1, it is a very simple temperature profile. For sample group 2, the graphite and the silicon carbide, it requires the already explained two-step procedure. First an hour, then perchloric acid addition, another half an hour. But this is what you get to see at the end. Carbon black, graphite samples, silicon carbide. What do you see? Nothing. So that means it's destroyed. It's completely mineralized. You do not even find small black carbonaceous powders. So this is a photographic image after transferring the sample into an autosampler vial and diluting up to 25 milliliters. And this is typically the time when you prove if the digest was complete. Shake the tube, hold it against the light and see, are there any particles in there? Dark particles, undestroyed residual carbon. Light particles, maybe undestroyed silicates. No particles, you've done a good job. Let me come to minerals and mining samples, also very important here in especially Western Australia. Minerals, a huge group of materials. We can divide into more or less two groups. One is classical, simple to digest, dolomite, carbonate-based rock material, calcium-based rock materials. They're quite easy to digest in aqua regia. You could maybe do this also on a hot plate. When we look at minerals group B, for instance, bauxite, talcum minerals, or silicon aluminum oxide materials, they are more difficult to digest and they require a different approach. So these are two groups that we would separate in the lab and we would run via two different methods for optimal results. Group A, like I said, aqua regia digest. Group B, the classical 4-acid digest. Maybe not the classical, but here was some water added. Why did we add water? In order to get a better solubility of the large amount of material. Also the temperature profiles, group A only took 220 degrees, 20 minutes ramp, 20 minutes hold time, whereas group B was taken to 250 for complete destruction. But again, within less than 1 hour, you can decompose 20 samples. These are the temperature profiles, nothing special about. What is what is worth mentioning is, if you look at the temperature profiles of all the vessels in the run, you see they are very narrowly following the predefined temperature. So this shows you that all the vessels have undergone the same temperature treatment and you can achieve the same quality of digest in all the vessels involved. Steel and alloys, we are still dealing with material testing. Also for this sort of materials we did tests with standard reference materials. Quite easy to digest, 200 milligrams. You do not need more because the samples are highly concentrated and they're very homogeneous. Digest simply with hydrochloric and nitric acid. Important when you add the reagents to steel and alloy sample, add the HCl first, because if you put the nitric acid on first, it would lead to a surface passivation of the steel material. If you do the hydrochloric first, it already starts attacking your sample before you start heating. Some samples may require the addition of hydrofluoric acid, and you will note that when you add the acids, there will be some reaction starting immediately with the steel samples, and you should wait for the first reaction to decay a bit so it cools down a bit, then add hydrofluoric acid, close the reaction vessel and go. Final example, we also offer another rotor type that I did not yet explain before. It is a rotor with 8 positions, which has as a specialty 8 pressure sensors on top. So this is a closed vessel digestion rotor, which is built for the highest temperatures and highest pressures. There are some samples requiring 260 up to 300 degrees centigrade. The 300 degrees we do typically in quartz vessels, whereas 260 we do in fluoroplastic vials. This is a very special design in the market, and it's made, for instance, for oil testing. We use it in many refineries which prefer this rotor type and this vessel because it has 100 milliliter vessels and they allow bigger sample weights to be processed. Another and even more challenging application is digestion of ceramics and oxides. So also here see a list of various silicon-based or boron nitride, silicon nitride ceramics, as well as oxide ceramics of titanium, zirconia, and aluminum. The sample weight for such applications is very low, only a few 10 milligrams, but that's sufficient because the material is very homogeneous. It's very important that the sample is ground to very fine powder, ideally much less than 50 microns, because the finer the powder, the higher the oxidation efficiency. And what you can see is also that the sample preparation chemistry varies amongst those 4 acids in various quantities. So these are optimized methods which allow the destruction of these ceramic materials in a time frame of 30 to 40 minutes plus cooling. So again, within 1 hour, such samples are destroyed. Just quickly mentioning accessories of the Multiwave 5000 for special applications. We offer a special rotor for micro samples. If you have just 10 or 20 milligrams of samples to digest, we offer 5 milliliter test tubes, 64 of them in one rotor. There are very special applications where we can do this. Evaporation accessory to get rid of unwanted acids prior to analysis. We offer a rotor for the drying of sample materials, which is often used in environmental and food testing applications. And we offer special appliance for microwave-induced oxygen combustion. And, like mentioned before, various kinds of organic chemistry reactions can be done as well. Just let me quickly mention the microwave-induced oxygen combustion. What we can do in this 8-place rotor, which is very, very special, and there's no other offer on the market for that, is that this is a cross-section through a quartz glass reaction vessel for the 8-place rotor. And we can load this quartz glass vessel through a port with oxygen of up to 20 bar. Inside the reaction vessel, there's a sample holder where our sample that we want to combust is pressed to a tablet, rests on the sample holder here. When we switch on the microwave will ignite the sample and it will burn by consuming up the oxygen which was preloaded in here. So we will end up with a little portion of ashes in here that is later on dissolved in an absorption solution which rests here at the bottom. So the whole process of combustion and absorption takes less than 10 minutes. And then you can destroy even very rigid, very hard to decompose organic substances. The most interesting thing we ever did with this combustion method was industrial diamonds that you cannot dissolve in acids, but you can burn them in oxygen. But we only had a very small quantity of those. Another application is the analysis of halogens in various kinds of samples. Here, halogens in coal. After such a combustion, you do not take these samples to an ICP, but you use, for instance, ion chromatography or ion selective electrodes for analysis of fluorine in that case. If you're interested in that, we can give you publications from several university groups that work with that. So far, that's Multiwave 5000, the main product of the analytical synthetic chemistry product line. Now, what if your requirements are different? I'll show you 2 alternative options to this microwave oven system. And the first option is our Multiwave 7000 system. It is not a conventional microwave oven, so you see it already looks different. It is a microwave heated autoclave with a so-called pressurized digestion cavity. I'll explain the principle later. Mostly important, the specifications of 300 degrees at 199 bar. Why is it not 200? This has to do with pressure vessel regulations. So 300 degrees, 199 bar. Also, this unit has an integrated cooling system, and you can run up to 28 samples in one run. You have various sample sizes and various vials that go into this pressurized autoclave cavity. Vessels could be either quartz glass or PTFE, reusable, or you could also use ordinary laboratory glassware as disposable, so in case you do not want to clean reaction vials. The closing and opening, loading and unloading procedure is largely automated, and also for this instrument a magnetic stirrer can help to optimize certain reactions. So how does this work? Compared to a classical microwave oven, we all know how it works. This pressurized digestion cavity works according to a different principle. You have a steel-walled autoclave chamber closed with a massive lid. Inside this chamber there is a load solution, very diluted acid or slightly acidified water, let's say. And inside these load solutions there rest the reaction vials with the samples and acids in there, and they are only loosely kept with caps with an opening. So we are pressurizing the complete autoclave chamber here with nitrogen or argon at the pressure of 40 to 70 bar. So this pressure will act upon the liquid here and will prevent the liquid from boiling. So you can also overheat it way above the boiling point at ambient temperature, and that's the benefit here. Microwave is fed in from the bottom, and via this load solution we achieve a very homogeneous distribution of the temperature to all reaction vials. And this is independent of the samples that are in there, independent of the kind and amount of acids that's in there. So it's a very flexible, the most flexible digestion principle that is available. It achieves the most homogeneous temperature distribution amongst all the samples in the process. And like I said, the temperature is independent from the filling. Whereas in a microwave oven, imagine a small portion of acid would only interact minimally with the microwave, whereas if you have a larger portion of acid, it would absorb a lot of microwave energy. So you should not vary filling volumes too much in the oven. Here it does not matter. Just explained the key benefits. Just have a look at the picture here. That's the digestion vial, and there's a simple plug-on cap that you put on top. That's the only closing action you need to do. The selection of racks and vial sizes, if you do micro samples, like in medical testing, blood, hair samples, you would prefer a small vial of 7 milliliters. If you do testing of large quantities of whatever kind of material, you can use an up to 80 milliliter vessel size, 5 of them in one run. However, it has turned out that an 18-place rack with 18 milliliter vessels is the most widely used ones. It's a good compromise between sample weight and number of samples in the process. That's the loading process. Put samples and acid in a vial, plug it with a cap, put it in a rack, put it in the liner with the load solution, and transfer the liner into the autoclave. Very simple 3-step procedure. Then the software will guide you through the closing action. There's just a manual metallic clamp that you need to close. Heating, cooling takes part automatically, and at the end you have again a software guided opening process, and you can take out the cooled vessel with a liner lift that brings out the whole beaker, the whole liner with the ready to analyze prepared samples. At the example of Multiwave 7000, let me spend a few words on how to approach to unknown samples. If you have a sample of unknown reaction behavior, what to do is, first you should at least know, is it inorganic, organic, and about its reactivity. You should have at least a good guess. When you start with small sample quantities only, and then slowly increase. So a good starting weight for various samples would be 100 milligram. I would not dare to start with 1 gram immediately, even if an instrument is specified for that in general. Then be careful and select the type and amount of acids, which must match with the analytes of interest, but mainly must match with the nature of the sample. And this is where a methods library, a methods handbook, application directories, application reports are of great help to the user. Sometimes it may be necessary to decrease the oxidation potential. At the example of cold syrup, I said let's dilute the acid. In some cases it may be required to increase it by the addition of perchloric acid as a strong oxidizer. And last but not least, it is a question of the appropriate temperature program that you can apply. Here's just a list of instrument-specific support that can ease your life when choosing a method for a new and unknown sample. In Multiwave 7000, we have more or less a list of 8 basic programs. And with these 8 basic generic programs, we managed to destroy almost all the samples this instrument is made for. So we have a coarse classification, is it organic, inorganic, easy or difficult, and we have special methods for food and petrochemical samples because we have a lot of users in these application sectors. So it's very straightforward in terms of simplification. Also the 7000 we have tested with pharmaceutical samples. I browse over that very quickly. 35 minutes heating to 250 degrees. Keep the temperature for 10 minutes and cool down. So within an hour the samples are digested and you see a similar picture. I've intentionally chosen pharmaceutical samples for all our systems to see that they can be done depending on their nature, and they can be done and will be done with very good recoveries and with small RSDs in the 7000 as well. One special thing which pharmaceutical customers are interested in is the analysis of osmium, which is most likely the most volatile element you have to deal with. And even the osmium is found at recoveries between 82 and 90% in Multiwave 7000 digests. This is really, I would say, a proof stone in terms of retaining analytes. Multiwave 7000 is the very high-end, instrumental high-end of sample preparation, but there are also labs that would never require 28 samples in one run, that would never require 300 degrees. They would more look for an economic solution, which saves lab space and which also can do very powerful digests. And this is the third member of the Multiwave family, which is the Multiwave GO Plus. It is an instrument made for easy and economic digestions. Also, this is not a classical microwave oven, but it has a specially designed direct multi-mode cavity where a metallic rotor rests upon a microwave applicator that applies microwave from the bottom, and the lid of this is closed and seals the whole microwave cavity afterwards. A very special design that helps for very efficient coupling of microwave directly to the reaction vessels. So it's the most energy efficient microwave applicator that you find in the market. And it's the one with the smallest footprint. It's only 36 centimeters wide. Also, this small unit comes with an integrated cooling unit to benefit from shorter process times, and the handling, I think, is most simple of all instruments in the market. it allows the digestion of 1 up to 12 samples in one run. So that's just a cross-section about the heating, holding and cooling phase. In heating, you say at the left picture, the microwaves approach the vessels just from the bottom. So they reach the vessel where the solution is, and so they are most efficiently directed towards the solution compared to a big oven cavity. This works very well for this small 12-place rotor. We utilize the same type of smart vent vessels like the big microwave oven, so the basic principle operation characteristics are quite the same. And also here we have the cooling fins and a built-in cooling unit that cools down within less than 10 minutes from operation temperature to below 70 degrees centigrade. So very efficient. Features we were already discussing. Let me skip this. Yeah, just to remember the parameters 200 degrees and 20 bar. And what we have here is a single vessel mode. We could even digest only one sample if we like. Whereas in bigger rotor systems, it always requires a minimum set of load to run it efficiently. What are the applications? You already guess because of the vessel type, the HVT rotor vessel. It's again food and feed samples. It's biological materials, it's standard methods, and it's also part of the pharmaceutical and geochemical testing sector. Again, the example of mixed food, like I showed it for the big rotor in the 5000. Again, you see these large variations depending on the different nature of samples, and the important thing, all they are taken to the same final temperature, to the same digestion efficiency, and see how quick the cooling is. As an example, environmental analysis, EPA methodology, US Environmental Protection Agency, method 3051, a very efficient one, prescribes taking a sample up to 175 degrees and keep it there for the rest of the portion of 10 minutes, just 10 minutes digest. And then there is a 7 minutes cool down phase. So this EPA method would have been accomplished, including cooling, within 17 minutes, which is, by the way, the fastest result that you can get out of a microwave digester. Example of soil leaching. Again, we tried a certified reference material, and the correlation of measured results with certified values is very good. Recoveries, good recoveries. So these were the 3 Anton Paar instruments for sample digestion. I've shown you a selection of applications. I would have had many more, but this would exceed our time frame. Just wanted to let you know, if you have samples for which Anton Paar does not yet have a method, very unlikely, but if it happens, we give application support. That means our subsidiaries, with the support of the headquarter labs, is prepared to develop methods for your particular sample. And we do this as a service to our future and existing users. And we do this with a lot of effort. So you can send us samples. You must attach a material safety data sheet. And we can do this in our application laboratory in Austria, including elemental analysis. We could do this probably locally for some samples, but most of the samples would go to Graz. We develop the method, send it to our local subsidiary, and it can be shown to you either in our demonstration lab or even better on-site in your laboratory. So this is just at the end of the technical part. Some of our users, you see, they come from various industries, from electronics, food, car manufacturing, beverages, petrochemical, pharmaceutical, electronics industry, wide variety. This is just a little cross-section. A very important group is testing labs like TUV, Eurofins, Intertek. These testing labs are now more and more concentrating on analytical services, and smaller companies try to dissolve their analytical lab and give the samples to third-party labs for analysis. Unfortunately, SGS is missing, but is definitely amongst our customers. It will go in here in my next presentation. Okay. So, at the very end, let me show you a few slides that you know the area where I'm coming from. Graz, Austria. Graz, the second biggest city of Austria. That's a view of our main square. Here in the center on the top, that's our landmark, the clock tower. It's a 300,000 people city. A lot of universities, high-tech companies there, and a very nice place to live. It's a very traditional place, so most of the houses that you see here are from the 16th century. There's a lot of architecture of that time, strongly influenced by Italian style Renaissance architecture. With beautiful libraries. This is, for instance, in a monastery, and it contains a lot of handwritten books. So we have precious cultural sites, either in Graz or a 1 hour drive out of Graz. You also find very modern architecture within Graz. So this is like an alien would have landed in the old city of Graz. This is our House of Arts, which was built in 2003 when Graz was the cultural capital of Europe. So even this is possible. In our south of Graz, in our drive south of Graz, there is a very nice wine area. In our north of Graz, there are beautiful mountains. So for hiking, climbing, mountain biking, this is an area that I like very much. Really beautiful. The area is blessed with a lot of natural water resources. So our nature is very well preserved. And even in the wintertime, water can be very challenging. Skiing is the national sports #1 in Austria. So, this is now the very end of the lecture session. Question, did we have any questions from outside for the short Q&A session? No questions so far. Questions from the audience here?
That's very informative. Thank you.
I have. So all the instruments have multiple position rotors.
Right.
In the event that there aren't enough samples for all the rotors, is it acceptable to run with only X amount of samples in there?
Right.
And if that is the case, do you leave the vessels out of position whilst you're doing that?
For instance, if we look at this 24-place rotor, you could load it with even only 4 samples and leave the other places empty.
Yeah.
What you anyhow mostly do is running samples in duplicates. So you have at least 2 vessels positioned. You could run, let's say, a control sample and a blank along with it, and you already have 4 samples to load. 4 samples is a minimum for this rotor. In this Multiwave GO Plus, you can also run with just one sample.
Right.
So if this is your major requirement, occasionally a sample to be done in a microwave, that's the instrument of choice.
Okay.
So it's just your normal rotor balance then? 1, 2, 3, 4.
Yep. Yep. So when you load the rotor, you should load it symmetrically. 4 at opposite positions, or 6 or 8 or 10, 12, whatever gives a symmetric load pattern is allowed. Of course, you could also place all in one row, but then they probably would heat unevenly. So for even heating, a symmetric load pattern is recommended.
Okay, thank you.
Welcome. No questions. Okay. Then we would move over to a short hands-on session here. These are the reaction vessels that I was talking about in the presentation. The HVT vessel just consists of 3 parts. The lower part that you put on the balance, add the samples and reagents. The sealing plug and the screw cap. And this is just hands-tight operation. You close it until this pin in the center is flat on the top, so you can see it and you can feel it. It's very easy criterion to see is it properly closed. That's it. It goes into the rotor. So you see it's very quickly to be done. The same applies for the vessel with a superior high pressure. Also there, just 3 parts, a very robust plug and the screw cap. Of course, you see the difference. This higher pressure vessel has a bigger wall thickness, and this users do not believe both have 50 milliliters. This is just a thicker wall here. This is why it looks bigger. So you load the rotor, and before you put it into the microwave, there is a rotor lid to put on top. Why that? Because you can imagine if you have reaction gases, maybe sometimes also acid droplets coming out here, they are safely collected here on this rotor lid. Then you take it and
Hands are always full, so yeah.
so this is a nice thing. Like I said, that's what users like, mostly like most, because that's really unique. Nobody else has this.
It's not about the technology, it's about the door.
This is what counts in daily life. Yeah. Microwave is a microwave, but the little details that ease your daily work, these are important. These are appreciated in the lab. Let me take out the rotor again. Of course.
Just, as the usual without samples. It's quite heavy.
It is about.
With the rotor.
It is about 7 to 8 kilograms.
The samples.
Yep.
In and out without. Yeah, 7 to 8.
But you could also load it inside the oven. If you say this is too heavy for being carried around.
Yep. So you leave the,
leave the rotor body in there and take out the individual vessels. At the end of the digest, it even has a push button that it moves by one rotor segment that you can always take out from the front position. That's quite easy to do. Oven cavity, like I said, is stainless steel, of course, with multi-layer PTFE coating. So you don't have any corrosion problems with this in the lab. We have microwaves, 2 microwave generators, 2 microwaves, one coming from the left behind this white plate. There's another white plate at the rear. And we are feeding microwave energy from 2 sides. And by this rectangular array of microwave irradiation, we get a very homogeneous distribution. You may ask, what are they doing with metal in the microwave? Usually you would not place metal in the microwave. On one hand, metal is very beneficial because of its mechanical strength. So a very thin metal wall gives the pressure stability to this PTFE vessel. It keeps it closed and prevents it from blowing outwards. So how does the microwave get to the vessel? From underneath. In this white area, this is the way where the microwave gets into the rotor body and heats the sample solution here at the bottom. So this is a very neat way of using metal for mechanical strength inside the microwave without affecting the microwave field too much. That's a specialty that only Anton Paar is using this kind of technology. What you see here are the safety hooks for the front door. They are engaging here, and during the process, if I would start the instrument now, it would be locked and cannot be opened by this or that door opener. When I close the oven door, the rotor already starts turning, and the instrument automatically detects which sort of rotor is setting here and would not allow you to choose a wrong program. So you can choose programs just for this rotor type. And depending on how many rotors you have in your lab, how many different kinds of rotors, you can stepwise activate all them in the methods library. Methods library, by the way, let's say we want to do food sample. It comes with a list of recipes for baby food, fatty food stuff, fats and oils, pet food, cat food, and plant material also falls under this category. Let's say, take the fat-rich food method, tap at more info. It says you can do 0.3 to 0.6 gram, 3 to 8 mils nitric, a little portion of water to reduce reactivity, and maybe some hydrogen peroxide.
And you said you had supporting documentation, didn't you? We can get supporting documentation
Of course.
On the methods and things.
What comes with the instrument is an application guide that gives you very generic guidelines for how to approach unknown samples. And you just can simply follow the information given here on the screen for the particular sample you would like to do.
I'm just thinking with the method development, we go and we select the program, that's fantastic. We do some of our samples, where's all the supporting argument for the method. So
Yeah.
That's good.
Yeah. You could choose any of our methods and modify it and store it as a modified method. You cannot alter the existing Anton Paar methodologies, but you can add your own methods to the existing library. What is also very useful, so when you're back at the main menu, is the video manual. Excuse me, just a moment. The video manual contains more than 70 video files that shows you all the handling steps, from installation, how to do an experiment, but also very important, cleaning and maintenance. So all these important things, but let's see it. Loading a rotor, for instance, preparing and starting. So it comes up with video clips directly on screen. Shows you the three different HVT rotors. Yeah. And you can fast forward. So weighing of samples directly at the balance. What you see here is an anti-static gun, which is very useful in order not to have samples caught to the vessel walls by static discharge. It's a very common tool.
Handy
And you also do the anti-static action to the sample. First to the vial, then to the sample, and then you can very nicely fill in even powdered samples into the reaction vial, which otherwise would be attracted by the vessel walls when you pour them in. Another thing is when you then, after loading, add the reagents, we recommend to turn the vials and to wash down the sample material down into the solution. There shouldn't be no sample parts sticking to the wall when you start the microwave process. Yeah, this should not happen.
Yeah.
That is what it should look like. Use anti-static gun.
Julie, no?
Things like that.
Yeah, that's good.
So that top that goes on, if you're digesting and you've forgotten to put that top on, do you stop the digest or just let it go?
No, it doesn't. Let it go.
Yeah.
The worst thing that can happen is that you have some spray and must clean the cavity. If you forget this every now and then, that's not an issue. It's not a safety issue. It's more a maintenance thing. There are definitely no operating conditions that can take you into safety critical situations. Most provisions are for maintenance, easing the maintenance and reducing the chemical load to the components. Yeah, this is it.
Thank you. No questions?
No questions?
No questions?
Oh, sorry, this one.
This one? Yep.
This one, thank you. In terms of the digest vessels and rotors, do they degrade with the number of cycles they go through the microwave?
Okay. Question was, do vessels degrade depending on the number of cycles? Of course they do, and it depends on the reaction conditions. If you digest, let's say, food samples with nitric acid, you can run maybe thousands of samples before you replace an instrument, before you replace a vial. If you do high temperature digests at 250 degrees with this 4-acid digest, including sulfuric acid, vessels will wear out faster and maybe last only a few hundreds of runs. You could detect this when the surface, the inner surface of the vessel changes, when it gets rough and particulate. And this is the time when you see you have to replace the vessels. They have a limited but very long lifetime.
Okay. So there's no more questions. I'd just like to thank you on behalf of Rowe Scientific and our clients. I'm sure everybody's had an opportunity to learn something, and it's a very comprehensive explanation and demonstration. Thank you very much.
Thank you very much to you, Brad, for having been the host for this little seminar today.
My pleasure. Okay.
Thanks a lot.
Thank you and goodbye, everyone.
Thank you.
Awesome.
Thank you. Quite in time.
Well, I was going to say, are we offline yet?